Thanks, everyone. So I'm going to talk about some QoS enhancements and some optic enhancements. A lot of these features actually already exist, but we're extending them to a number of other platforms. So let's go ahead and get started with IP ECN. So this is explicit congestion notification. So just as an overview of what IP ECN is, this is, it's an extension to the IP TCP protocol. You can see it's defined in RFC 3168, but it really is used to allow end-to-end communication or notification of network congestion, telling the sender or receiver to throttle back traffic because there is network congestion. With regards to use cases, let's talk about Ethernet-based storage area networks. So with Ethernet-based storage area networks, we deploy these solutions using RDMA over Converged Ethernet. And this, of course, comes in both the V1 and V2 protocol. V1 requires the data center bridging protocol suite. And of course, V2 implies that there's a layer 3 hop in the network. And these are the solutions where we're going to be using DCB, but we're also going to be leveraging on this IP ECN protocol also. Also, we can see here at the bottom here a number of potential type RoCE-based workloads that we can be seen in the market. So SMB3 Direct, Azure Stack, Oracle RAC, Storage Spaces Direct. These are all common RoCE-based workloads. And RoCE v2 and ECN is now supported on the 8325, the 8360, and the 8400. So it's supported across our entire primary data center product line. Taking a step back and looking at the RoCE v1 and v2 protocols themselves. So of course, the data center bridging protocols contain a number of protocols: priority-based flow control, ETS, data center bridging exchange. And these are all used and leveraged for RoCE v1. But of course, and like I said, in the RoCE v2 type solutions, we're going to be using those data center bridging protocols, but we're also going to be layering on ECN over those routed links to allow end-to-end host communication of congestion. And of course, so with 10.7, what is new is we've extended IP ECN to the 8325. So now, of course, we can, like I mentioned, we've got the full RoCE v1, v2 suite on our primary data center switches, the 8400, 8325, and the 8360. Just some details about IP ECN. So ECN is about notifying the network or the reaction points about congestion. Of course, the goal, of course, is to reduce packet loss and delay by telling the communicator, the reaction points, to throttle back their traffic. And of course, the ECN bit is actually communicated using the ECN bits in the packets. You can see here on the left, when it's marked as a 1-1, of course, that's telling the endpoint that there's congestion that's been experienced on the link. In fact, we have a better image of that. So it marks the packets using the least significant bits in that diff-serve field. And these threshold profiles, you can optionally configure queue utilization thresholds as an ECN marking for this packet. And it can be applied per port. Of course, when we emit a configuration for a queue and a threshold profile, that really does mean that queue will not be configured with a threshold, right? And threshold profiles are considered strict, which means when that action always occurs, the threshold is going to be exceeded.
Steve, I'm sorry to interrupt. We have a number of people in the reporting they can't see your screen. Could you maybe stop sharing and reshare your screen, see if that fixes it?
Yeah. So I just reshared the screen again.
Okay, I can see it now.
Hoping you guys can see it. So I'll go ahead and continue unless you guys keep getting some notifications. I just wanted to give you guys an end-to-end view of a data center bridging solution with IP ECN layered on top of it. So here we have, an end-to-end solution where we're doing layer 2 from the initiators and the targets to the directly attached switch, but we've got a layer 3 hop in the center. So we're going to be deploying the data center bridging protocols like PFC, ETS, and DCBX. We're going to be applying these using queue profiles and schedule profiles, but also because of this layer 3 hop in the center, we're also going to layer on IPECN, which, like I mentioned, of course, marks that least significant packet in the diff-serve field to tell the initiator, hey, there's a congestion on the link, so just throttle back your traffic a little bit. So the way we can configure ECN with the 3 switches that we support is slightly different on the 8360 and the 8325. So of course we would start by creating a QoS threshold profile. And then once we get into that threshold profile with the name that we've given it, with the 8360, we would apply an action to a queue, and this would be an ECN action. And the threshold is defined by a percentage value. And on the 8400 and 8325, the threshold is defined by a kilobytes value. And of course, we can turn off the threshold profile by doing no QoS threshold profile in the name. And then, of course, we can actually apply this threshold profile either globally or at the interface level, and we can see that at the bottom. So globally, it's just simply applying the QoS threshold profile in the name. Of course, we can use the no command to turn it off. And then, of course, it's the same thing once we go into an interface. We could apply it only to that single interface using that same command. I wanted to give you guys just a view of an applied threshold profile. So you can do the show QoS threshold profile, and it shows that the ECN profile has been applied. And then, of course, if I add the ECN name, I can get details about what's actually been applied and what ports it's been applied to. So for resources, the CX QoS configuration guide, and I actually should have listed it here. Of course, we have a DCB guide. I'll actually add it to the deck here on a Rubipedia that I can share with you guys. Flow control. So let's talk about flow control and what's new with flow control. I'm going to talk about link level flow control and priority flow control a little bit. So link level flow control, this is a mechanism that temporarily stops Ethernet traffic being transmitted across a device. Of course, the goal, of course, is to avoid packet loss, and that's the goal with both of these actually. Link level and of course priority-based flow control is similar, but it operates on individual priorities instead of pausing all traffic on a link, like link level flow control does. PFC pauses traffic only marked with a certain priority. So here, of course, is an overview of Ethernet link level flow control, stopping transmission of traffic over the entire length. Like I mentioned, the goal, of course, is to avoid packet loss. And of course, the receiving station can signal the sender requesting the suspension of a transmission until that actual receiver catches up. This is actually implemented at the data link layer. And then, of course, the difference here with PFC, like I mentioned, is PFC only sends that pause frame to traffic that's marked with a certain priority code point. Just some notes, of course, we're going to be using the 802.1p priority, and the IEEE strongly discourages using the priority code point 0 for PFC. Typically, the priority code point 0 is not used for PFC. And then, of course, we would actually implement PFC using the queue profile map. I have some config. So what's new? Okay, so what's new is we've added receive and transmit link level flow control support to the 8360. And we've also added PFC plus LLFC working in conjunction on the 8360. And we've also added 2 PFC priorities. Now, when we're talking about flow control, link level flow control is only going to operate correctly when both the ingress and the egress interfaces have that enabled. When we have a lag interface, all member ports of that lag need to have the same flow control configuration. And it's good to note that replicated traffic like broadcast, multicast, and mirroring cannot be guaranteed for lossless. So lossless traffic in these solutions is just for unicast traffic. Lossless behavior isn't supported with VSF stack configurations. And for interfaces that do auto-negotiate, link level flow control is subject to that negotiation. So both links must negotiate that same flow control, right? And for interfaces that don't auto-negotiate, the link level flow control is always applied, and the user is really responsible for ensuring that both ends of that link are configured in that same mode. So we can actually take a look at this link level flow control. So of course, on the 8325 and 8360, we can enable flow control at the interface level, receive flow control. Of course, if we want to do the receive and transmit, we would do the RX-TX. And then for priority-based flow control, you would be applying that, that configuration to a priority. So priority 2 in this example. Of course, to disable these, we simply add the no command before each of the commands to disable any of them. And of course, like I mentioned, the 8360 now actually does support 2 PFC priorities. So we could actually have 2 separate code points being treated as lossless with PFC on the 8360 now. So here is just a simple example, of course, of the receive and transmit flow control that's now been enabled, and we can see that when we do the show interface 115 command. Again, for resources, the QoS configuration guide as well as the CX interface configuration guide are great resources. The next thing I wanted to talk about is some optic and AOC updates. So for optic updates, we can see here the 8325 and the 8360 on this first page with our 1 gig, 10 gig, 25 gig. You can see all the optics that are supported all the way through 10.7. But now with 10.7, we're enabling a number of AOC cables on the 8360. They've already been enabled on the 8325 with 10.6, but we're now enabling a number of these AOC cables for the 8360, and you can see the 40 gig AOC cables as well as a 15-meter breakout cable. And then of course we're also enabling 100 gig CWDM optic as well as 100 gig AOC cables, as well as take note an ER4L optic. And then of course we've got a couple more additional optical breakout cables, 7-meter and 15-meter, that are now supported. And I have another optic I want to show you guys. So this is our QSFP28 to SFP28 adapter. So this is a use case. This is an adapter that enables us to convert a 100 gig port to a single 25 gig port or a single 10 gig port. And this is now supported in the 8360, the 8325, and also the 8320. So it's a simple use case, right? I've got a 100 gig port and I just simply need a 10 or 25 gig connection into a host device. This adapter will convert that 100 gig port into either a 10 or 25 gig port that I can use with my 10 or 25 gig optic. There are a few restrictions that we should note. Here's the SKU. On the bottom line here, it's for the 8320, 8325, and 8360. There are a couple other types of these adapters on the HP price list, but we don't have any planned support for those. You can see when you use when it's used in a QSFP Plus port, it'll support, of course, 10 gig SR, LR, ER. But if you use this in a 100 gig port, you can support, of course, SR, LR, ER at 10 gig, but also 25 gig, so SR, LR, as well as ESR. And everything is auto-detected, so there's no configuration when you need to configure it between 100 gig or 40 gig. And of course, there's no reboot either, so that's good. Now, this is kind of one of the caveats I wanted to really highlight, so save this in your file. On the 8360, this optic is actually only supported in certain ports. So take note of that. You can see the green pluses here, the port 35 and 34, as well as, of course, on the 12 port 100 gig model, the 6 ports on the right are the ones that are supported. So take note of this. Okay, and next I wanted to talk about some updates to minimum bandwidth guarantee. So as an overview, minimum bandwidth guarantee is a percentage per port of the amount of bandwidth that's going to be guaranteed for a particular queue. The scheduler is going to service non-empty queues in a strict order up until their minimum bandwidth. And of course, if a queue is not requesting bandwidth up to its configured minimum, the leftover amount just joins the free servicing pool. A little bit more about minimum bandwidth guarantee. So the schedule profile is used to determine the order in which queues actually send packets. And of course, depending on the model of the switch you're using, those schedule profiles may be strict, DWRR, weighted fair queuing, guaranteed minimum bandwidth. And take note that queuing delay and jitter can really affect the quality of things like voice calls. So to prevent these conditions, voice calls are typically placed in the highest priority queue, right? And using strict priority for all queues might be good for voice traffic, but that does really increase the risk of starvation because lower priority queues may actually be taking that bandwidth. Guaranteed minimum bandwidth for all queues also would be fair, at least to the lower priority traffic, but of course we're still at the risk of delay and jitter. So combining these two together actually helps solve both of these problems for us. So the highest priority queue, that's Q7, of course, this is where we're going to use strict priority queue. And of course, the remaining 7 lower priority queues will simply leverage guaranteed minimum bandwidth. Of course, on each round, the scheduler is going to check for that highest priority queue, and it's going to send packets to that highest priority queue. But when that highest priority queue is empty, the scheduler will then use guaranteed minimum bandwidth to fairly select the next packet that's going to be transmitted. So here's some guidelines, and you'll take note that this minimum bandwidth guarantee feature has been added to the 8360 with 10.7 and the 63 and 6200. Like I mentioned, the scheduled profile is the one that determines which queue transmits a packet. And then, of course, the switch is automatically provisioned with a factory default schedule profile. There has to be a schedule profile defined on all interfaces at all time. That's why it actually comes with a factory default one already assigned. And of course, like I mentioned, guaranteed minimum bandwidth really apportions that available bandwidth amongst all those non-empty queues. And of course, the scheduler is going to service those non-empty queues in strict order up to their minimum bandwidth. And then, of course, if there's any remaining bandwidth, the scheduler will service any of those non-empty queues, the remaining non-empty queues. For configuration, we're going to first, on the 8360, 6100, 6200, and 6300, we're going to create a scheduled profile. In this example, it's called VoIP profile. And then once you're in the profile, you can actually start assigning the configurations to the different queues. You'll see here, this configuration shows strict QN7 for our VoIP traffic. And then we've got a minimum bandwidth guarantee of 10% for the remaining queues. Of course, if we want to turn this off, we could do the no queue schedule profile command. And then, of course, we would apply this profile either globally, using the apply QoS-Q profile command, or we would apply it to the interface. And of course, to take it off the interface, you would do the no command. Here, I wanted to show you an example of a queue profile that's been deployed. You'll see the VoIP profile has been applied. And if you do the show QoS schedule profile with the VoIP profile name, you can actually see the configuration, and you can see that configuration with minimum bandwidth. But we have to take note that minimum bandwidth cannot exceed 100%. But you can actually configure it that way. So if you were to configure it that way, over 100%, like we see in the lower left here, we've got 50% on the bottom, and then there's another, 70 or 60% up above. So we're over 100% here. Now, if we do the show QoS schedule profile command, you'll actually see that it's marked now as incomplete rather than applied. And if we actually did the show running config command, we'd actually see a notification in the running config warning us that the actual schedule profile has been the factory default, because this schedule profile is incorrect, essentially. And again, for resources, the CX QoS configuration guide, we'll have this in the 10.7 update. And so the next one is egress port shaping. So this has been added to the 8325. Egress port shaping, it enables us to, port shape an interface to less than what the line rate of that interface is going to be. So when we're doing egress port shaping, you enable the shape, the aggregate traffic through a port that is going to have to be less than that line rate of the port. And of course, you can configure these interfaces to shape this traffic based on the bandwidth of the total interface bandwidth. That's what we're going to be concerned about. We look at the details on configuring it. It already exists on the 8320, the 8360, the 8400, as well as the 6000 series, but we've added it to the 8325 now. It's configured by specifying the desired bandwidth rate in kilobits per second, and you can see here a few of the models. The data center models also support a burst size configuration. If you don't configure shaping on an interface, the default shaping rate is going to be at 100%. And of course, the actual configured shape rate and burst can be found by using the show interface commands, which I'll show you in a few slides. Here we go. So when we're doing egress port shaping, we can see an example here on port 118. This is for the 86,000 series and the 8360. We can do egress port shaping using kilobits. So we can see the command here, QoS shape, and then 100,000. But on the 8320, the 8325, and the 8400, we also support the burst command. So you can also add a command after that would support the burst. Now in the lower example, I wanted to show you, because this is an example where both egress port shaping and egress queue shaping are configured on the same port. In this example, it's port 118. Because both of these are actually configured on the port, the minimum of both setting is what's going to be actually configured in the hardware. So based on this example that you see here, where we've got Q7 max bandwidth with a 300,000 and a burst of 120, but I also have a QoS shape command directly on the interface with a QoS shape of 400,000 with a burst of 80. So because of this configuration, the effective bandwidth for traffic on Q7 here is going to be 300 megabits, but the burst isn't going to be 120. The burst support for that queue is going to be 80. So I hope that made sense. And here, of course, we can do the simple show interface command, and this is where you can see an easy example of the QoS shape and the burst that's actually been applied to that actual interface. And again, for resources on this command for 10.7, it'll be in the CX QoS configuration guide.